Hello everybody, my name is Viacheslav Adamchuck and we were going to talk about proximal soil sensing, and this presentation was developed as a complementary to other talks related to geophysical instruments used in agriculture. First of all, I wanted to talk about a few definitions. Geophysics is the physics of the Earth and the environment in space, also the study of Earth using quantitative physical method, and which is relates to an array of instruments used in agriculture. But actually, the area of proximal soil sensing is a little bit bigger, and it includes all the technologies developed to measure the physical, chemical and biological properties of soil when places a sensor in contact with or at a proximal distance, usually defined as less than 2 meters, to the soil being characterized. In terms of types of proximal soil sensor systems, there is a large variety, and they normally can be subdivided by the mode of operation. Some of instruments can be used in mobile mode, some just stationary. Also, measurement can be invasive or non-invasive. Non-invasive means that we don't necessarily disturb soil, and invasive we need to either excavate soil for further analysis or penetrate through soil and make measurement in situ. In terms of energy release, some sensors do need to provide some sort of electromagnetic signal to the soil in order to get response, and some sensors just record energy emitted by soil or reflected by sunlight, reflected sunlight, or things like that. And one of major inference is a major division between different sensors is the inference, whether we call sensors that they can measure organic matter texture or other specific agronomic values that we are interested in, or we are predicting those values indirectly through more or less complex relationship that sometimes we cannot even trace for a given data set. Despite these subdivisions, there is a variety of types of sensors that have already been used in practice. Again, the list that I have on screen right now, it's not all the sensors that have been attempted for use, but those are the most popular that we see people talk about. So first of all, it's sensors that can be used to measure soil topography, which is one of major data layers, and right now with RTK GPS available, it's become more and more popular. Apparent electrical conductivity and resistivity sensors, which there are 3 types: galvanic contact resistivity method, capacitive coupled resistivity, or electromagnetic induction. That's quite popular. Ground penetrating radar. Also, when we talk about electrical conductivity sensors, we discuss, we basically mean ability of soil to conduct electrical charge, but dielectric sensors, they are focused on ability of soil to accumulate electrical charge, and there is a family of those sensors as well. Optical soil reflectance, and that relates to the large range of electromagnetic spectrum of the data that we can record using either photodiodes or different type of spectrometers. Definitely gamma ray spectrometry, mechanical sensors, Ion-Selective Potentiometry, or chemical sensors. And in this presentation, I'm going to omit the first 3 types of sensors that probably discussed in details in other presentations in this webinar, and focus on the later part of later sensors. So in terms of dielectric sensors, there are several different probes that are already available on market for on-the-spot measurements, but there are also developments in terms of on-the-go sensors, and this is one of prototypes. Here you can see one of calibration curves when we see the change of capacitance, which is then relates to voltage of the soil surrounding a couple electrodes. In this situation, one electrode is split between two, and gravimetric or volumetric water content. This graph illustrates calibration with a variety of soils from almost pure sand to 36% clay. So when we try to calibrate sensor for volumetric water content, we got standard error of measurement about 4%, and gravimetric water content standard error of measurement around 3%. Well, in terms of electromagnetic spectrum, as I mentioned before, there is a variety of instruments that were developed to target particular part of the spectrum, and those that have been used in agriculture for a variety of projects, either optical sensors or gamma ray spectrometers, that I'm going to discuss a little bit further. So Tokyo University of Agriculture and Technology built probably one of the first online spectrometer, and it's actually a combination of a variety of sensors, CCD camera and several spectrometers, and even load cell and EC electrodes, and it has been used to collect spectra data, and in some of studies was quite successfully used to predict a dozen of different parameters that they were measured in a particular site. The instrument that is commercially available is from Veris Technologies with NIR Spectrometer. It's a combination of ocean optics and Fumatsu spectrometers that cover a majority of wavelengths from blue to near-infrared. And the special feature of this instrument is that interface between optical components and soil itself is a sapphire window that's drugged at particular depths, and users can obtain spectra continuously as they go through the field. And here is an example of using spectral data to predict carbon or organic matter. Those two parameters probably would be on the top of the list of what one can observe when using high density optical reflectance measurements of soil. Going to mid-infrared spectroscopy, online measurements that can be produced on the go have development in that area have been a little bit slow, partially because most of spectrometers, they are not really developed for field deployment. But the one that you see on the picture, it's a prototype spectrometer, and it has been developed for one of missions on Mars, and it showed pretty good performance in several laboratory studies, and it's quite durable and not very expensive unit. And the major properties that we were able to separate is soil texture. Here's a few examples of visible near-infrared spectroscopy and mid-infrared spectra. And with mid-infrared spectra, the two properties that we were able to observe is percent sand and silt and clay. And the most interesting feature is that we were able to use this instrument to calibrate using dry soil and then make predictions using wet soil. As a matter of fact, moisture is one of the biggest problems when it comes to calibrating spectral data, and there are several methods already been developed how to take into account for difference in soil moisture, but with this particular instrument we saw that it wasn't actually necessary, but we still have several additional tests to do in this area. From practical implementation, of course, spectral data requires large data storage capacity, long processing time, and and equipment is quite expensive. So there is a little bit of discussion of what end product can be used within farming community, and multispectral system seems to be a winner in this case, when we have a set of light emitting diodes and photodiodes in configurations that can also measure at particular depths light reflectance. And normally we're interested in this red and infrared part of the spectrum. That's the bands that have most informative the informative value is the greatest when we talk about organic matter or carbon. And here is illustration of another instrument also developed by Veris. In terms of gamma ray spectrometers, there is again several products that have been used for in situ measurements, and the one that have been popular for on-the-go measurements is shown here in the photograph. It's the MOL, and the way gamma ray can help in agriculture, that we can identify spikes of three particular isotopes, potassium 40, uranium, thorium, and definitely a total count of from this instrument, and either individual combination of these parameters have been quite well related to soil texture and cation exchange capacity and things like that, like any other geophysical instruments. And this spectrometer is also passive time, like soil is already radioactive material that we are testing. And this instrument is suspended at a particular height above soil, so it's relatively easy to collect data just from a technical point of view. Further, there is a very large number of mechanical sensors. They have been developed as a prototype system, and it basically relates to the mechanical impedance of soil when we try to penetrate through soil profile. One of challenge has been to differentiate different depths. It's one of instruments that we developed that had 3 shanks and a 4 shank for soil metal friction, and you can see a map where we can clearly identify special patterns that's related to both area compacted area, where we have increased bulk density, and difference in soil texture that normally relates to available soil water during mapping. This is another simpler system where we use planter stabilizer just to measure the depth of penetration under constant load, and that's also have been quite promising instrumentation for measuring bearing capacity of the soil, so we can see what is expected compatibility of soil rather than what we have as a final effect, really compacted soil or dry and compacted soil that would definitely cause a high mechanical impedance. Because moisture is a very important factor, and also organic matter has an effect on soil mechanical resistance, there is a tendency of combining different instruments in one system, and in this illustration you can see a soil mechanical resistance profiler, and it's a single knife, but it has an array of strain gauge transducers that can actually predict model of soil mechanical resistance distribution forces that act on this instrument, so we can see if more restricted layer is on the top of profile or lower in the bottom. And we also have soil optical reflectance. This situation we were measuring blue and red light reflectance, and a capacitance-based moisture sensor on the back to compensate for differences in soil water content. How this type of approach can be deployed is predicting soil compaction, bulk density. You can see a map of soil water content, soil moisture, obtained using capacitance sensor, and a map of uniform of soil mechanical resistance. I think it's an average force that we show on this map, and both do not have very strong relationship to bulk density. But if we combine them together, then we have somewhat better predictability and perhaps some additional data layers that might help to get those predictions even better. Now, in terms of Ion-Selective Potentiometry, that's one of examples where sensor really have direct measurements. I mean, we are talking about potential generated by glass when we have hydrogen ions penetrating inside the glass, or antimony, as we are using more for on-the-go mapping technology. In this situation, periodically sample is collected from predefined depths and brought in contact with several different Ion-Selective electrodes, and then when measurement is stable and recorded, aligned with GPS coordinates, then we go for next sample. And it's also been part of another instrument developed by Veris Technologies, soil pH manager, which can do mapping of soil pH on the this map illustrates traditional 1 hectare grid sampling for soil pH mapping and high density on-the-go mapping, and we can definitely see much more detail on the spatial pattern for on-the-go mapping, and several studies show that it's more accurate than any sort of interpolation of coarse grid sampling. And normally in practice we see practitioners use about 10 to maybe 15 measurements per hectare in commercial applications, and then they use that data to derive soil pH maps and lime recommendation maps and things like that. To kind of summarize this talk, I want to mention that there is emphasize that there is a variety of different sensor platforms available, and here my pictograms that you can recognize some of them. There is a variety of soil properties that we want to predict using these different instruments, and most of the instruments have an indirect relationship with these properties. The real challenge today is to find what relationship are the strongest, and actually find out what the correct combination of different sensor systems to address a particular soil property of interest. Here are a few tables that again summarize how different sensor types have been reported to directly or indirectly predict various physical soil properties. The same information can be found with regard to chemical soil properties. As an example of this sensor fusion approach, when we combine different sensors and different methods in the same system, we can unify in one platform, and it's already been commercial platform, soil reflectance, soil pH, soil AC mapping, topography mapping, because we can have RTK level GPS, and definitely we need to involve a laboratory with targeted soil sampling strategy to calibrate these sensor systems against properties of interest that we have, and it's the process itself of how to integrate all measurements together and tie it to calibration data. It's still there are several different practices, and what's the optimum is still to be decided. So here is an example of a system that combines EC, soil pH, and optical reflectance all in one equipment. So you can see the sampling cycle. And really, the biggest challenge, as I already mentioned today, is to get all this information that we get from sensor data and topography from the lab, integrated with yield data, with remote sensing imagery, with laboratory data, farmer experience, and have information that can actually help farmers either to go for systematic changes, best management practices, or implement variable rate technology in the way that will definitely increase the bottom line of their production system. So in summary of this presentation, proximal soil sensors can provide high density information about soil properties. Many sensor approaches are past the initial commercialization stage, and a number of systems available on the market in different countries around the world. Sensor fusion provides the ability to separate various effects, and that's where, in my opinion, biggest research emphasis is needed at this time. Site-specific sensor calibration and validation are essential steps in the mapping process, and laboratory soil analysis is still required as a supplementary practice to adopt proximal soil sensing in used in production agriculture, which is getting more and more popular. This I will be ready to answer any questions. There is my email on the website, and should be connected and ready to discuss this material during webinar on February 18th. Thank you very much.